Morning, good afternoon, and good evening, everyone. So today we're going to be continuing our linear algebra series, and we're going to go a bit back on the concepts of lines and matrices. Okay, so again, it's been a while since I've posted, and pretty much I think throughout the linear algebra series, I've been going a little bit too fast. So here I'm going to take it slow for once, also because I'm reviewing for my midterm, and I think it's good to take it slow and really learn the concepts behind everything. All right, so enough yapping. Let's just hop right into it. So now we're gonna talk about lines, or actually, shoot, no lines. Already went through that. Linear systems and matrices. Right. So systems of linear equations arise naturally in many applications, but the systems rarely come in what we call echelon form. Now, in this section, we develop a method for converting any linear system into a system in echelon form so that we can apply back substitution. So the idea is we want to convert a system into echelon form so that we can easily solve for the variables or for the unknowns. And so to get us started, let's do an example. Let's consider do a projectile motion problem. So say we have a cannon, sits on a hill, cannon on a hill. I'm not gonna write like good English. I might write broken English. It sits on a hill, and this cannon fires a ball. Right, fires a ball across a flat field. My screen. So this is a very ideal situation. Basically, you have this cannon, fires a ball on this flat field. It, that's the idea. Right. So the path of the ball is known to be approximately parabolic. So if we graph that, something that looks like that, and so can be modeled by a quadratic function. So let's just say path of ball is modeled by, and let's just write that. So it's e to the x. I wonder what e means actually. Textbook just tells me what to write. Here we see a typical quadratic function. Oh, here it says what e is. So where e is elevation. So basically, pretty sure that's the height of the ball, right? And that's in feet over position x. So we plug in some x value, we get the elevation of the ball at that particular x value. Right. And we say ABC, or just write it like this. Set of these things are real numbers. Okay, what else can we say? So figure one, shoot. Right, figure one shows the elevation of the ball at three separate places, since every point on its path is given by x e to the x, or x e of x. Data can be converted into three linear equations. So let's actually write it out. Okay, see. That's the graph. Then here are my linear equations. So we have these points, right? So we can say one of them is e to the 10, which gives me 117. And so we just plug in 10 to x. So we would get, in this case, 100a plus 10b plus c. That's one of them. You can also plug in this point here. So I plug in that first point. So another point could be 171, or should not 171. It's 50, which is 171. Then we write that out. So 30 squared is, I think, 900a, 30b plus c. And then we have another one, another data point here. To the 50 is 145. 50 squared is, my goodness, to 500, 50b plus c. So here we can see that we have three linear equations, and so we actually have a linear system, right? And this system apparently is not in echelon form, so back substitution is not easy to use here. And so we will return to the system shortly. So we'll return to that. We'll return to that in a bit. For now, we'll talk about elementary operations. And I think we did this in the past. Right. So what are elementary operations? So we can actually transform a linear system using some sequence of elementary operations. And so each operation produces a new system that is equivalent to the old one, so the solution set is unchanged. And we have three types of elementary operations, right? So what we're saying is we use elementary operations to a linear system to make it in echelon form. I'm just gonna put it out there. We use these sorts of stuff to make it in echelon form so that we can use back substitution, which is easier. But the solution set or set of solutions is unchanged. So even though we use these elementary operations, these linear systems don't change, right? Okay, so one thing we can do, so I'm just gonna write them out, so we can interchange two equations, basically switch two equations. Right. We can multiply an equation. So basically scale it. But when we multiply, it has to be by a non-zero constant. So it can't be zero, basically. And lastly, another thing we can do, these are not in order, by the way. We can add a multiple of one equation to another. So I'm going to show what all of these mean in a bit. Actually, I'm going to show them now. So let's do example one. Here we're being asked to find the solution set. So it's a collection of all solutions. We're going to find a solution set of linear system. Right, so here's the linear system. We have x sub 1, x sub 1, minus 3x sub 2 plus 2x sub 3. And we're going to equate that to negative 1. Then we have 2x sub 1 minus 5x sub 2 minus x sub 3. We're going to equate that to 2. And then we have negative 4x sub 1 plus 13x sub 2 minus 12x sub 3. And we're going to equate that to 11. So this system is non-echelon form. Now, if we go back, what does it mean for a system to be an echelon form? It means, well, pretty sure I have it in my notes. But basically, it has to have a leading variable. So here are the properties. Every variable is a leading variable of at most one equation, right? If we look at the linear system, we see x sub 1 being a leading variable to 3 equations. So we know that's not an echelon form. It's not an echelon system. And when it's an echelon system, it can only be, if we solve the thing, if we solve the system, then it can only lead to 3 options. It can either have no solutions, it can have exactly one solution, or it can have an infinite number of solutions. Right. And yeah, that's a theorem, basically. Okay, so going back to our example here, how do we want to find the solution set? So we want to eliminate the variable x sub 1 in the second and third equations so that we can leave x sub 1 as the leading variable in only the top equation, right? Because we want it to be in echelon form. So I'm actually going to go a bit fast here. I'm going to immediately do it as a matrix. I know it doesn't tell me to do that yet, but it's really simple. So here's what we're going to do. For matrix, all we need are the coefficients of each equation, as well as their constants on the right-hand side, right? So what are the coefficients? We have this one, 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 this one. Those are coefficients. So we're going to write them out. See, the thing is, we're also going to do elementary operations, but we're going to do it a bit quicker so that we don't have to write the x sub 1 to 3. It's pretty tedious work. Right, let's just do this. So you can see a pattern that I'm doing here. Yeah, I know. I went beyond what the textbook's telling me. But I'm going to do it this way, right? So what is this? We call this an augmented matrix, right? So we're given the coefficients as well as the constants on the right-hand side, and we have this vertical line. Okay. And then we do this symbol here, which looks like a tilde. It just means equivalent to some new augmented matrix that we haven't discovered yet. So we're actually going to do an elementary row operation here, right? So we want to make these things 0. How do I know? Well, if we make these 0, then we know it's in echelon form. Why is that? Because again, if we look at the properties, every leading variable has to be in at least one, no, in at most one equation. So we have a leading variable here, x sub 1. We have a leading variable here, x sub 2. And we have a leading variable here, x sub 3. And we can solve for everything if we just back sub or back substitution, right? Okay, so what am I going to do here? I'm going to start by eliminating this thing here. So I'm going to multiply row 1 by 4. What do I mean by row 1? I mean this, row 1, row 2, row 3. Sounds intuitive, right? Row 1, row 2. This is how we write it. Row 3. Okay, let's just hop right into it. So I'm gonna multiply 4 to row 1. That means everything in row 1 is gonna be multiplied to 4. That's one of the things we can do, right? Multiply an equation by a non-zero constant. 4 is a non-zero constant. And then we're gonna add it to row 3, and we're gonna put the sum of that in row 3. So let's just try it. So I'm gonna multiply 4 to row 1. That's gonna be 4. 4 times 1. 4 times negative 3, negative 12. 4 times 2, 8. 4 times negative 1 is negative 4. Row 2, we just keep it as it is. Nothing happened here. And then we're going to add it to row 3. So 4 plus negative 4 is 0. Negative 12 plus 13 is 1. 8 plus negative 12 is negative 4. Negative 4 plus 11 is 7. Right? And the cool thing about this, since we just multiply these by 4, we can actually change it back, because it just means the same thing. All I did was scale it so that I can make this thing a 0. And then same idea. I'm going to make these two zeros. So usually my trick here is I would like start from the first column at the bottom row and work my way up. So I'm going to make this one a 0, then this one a 0. And then this one is 0, then this one. So here I'm not going to make this a 0 anymore. I just need these 3 to be a 0. These 3 numbers to be a 0. Right. Let's just do it again. I'm going to make row 1, 2. Right? So I'm going to multiply 2 to row 1, subtract to row 2, assign that to row 2. Okay? So I multiply the first row by 2. So it's going to be 2, negative 6. I'm going to go a bit faster. 4, negative 2. And then you subtract it to the second row. Minus 2, 0. Actually, I could write row 3 right now. 2 minus 2, 0. Then we have negative 6 minus negative 5. So that's 5 minus 6, that's negative 1. Okay, some basic arithmetic. 4 minus negative 1, that's 4 plus 1, that's 5. And then negative 2 minus 2, it's negative 4. So I hope I didn't mess anything up. Let's see, 2 minus 2, 6 plus 5, 4 minus negative 1, negative 2 minus 2. Yeah, got it. And then again, I can rescale, call it scaling to be honest. I can write it back to how it was. Right. Now, oh, lucky me. I could immediately make this a 0, right? Can I do it? I have a negative 1 in row 2. I'm gonna keep row 1 as it is. Done with that. Row 2, on the other hand, I could basically add it to row 3. And then assign the sum in row 3. So this is going to be 0 plus 0, 0. Negative 1 plus 1 is 0. Actually, I'm going to keep this. 5 minus 4 is 1. Negative 4 plus 7 is 3. And there we have it. We have it in row echelon form. How do I know? Properties again. We have a leading variable, each row, of in at most one equation, right? So we know that's an echelon form. I hope that makes sense. The caveat of this property? Well, if we have a variable that's not a leading variable, that's okay, right? But the idea is if we have a leading variable, it has to be the leading variable of at most one equation. That's what makes it in echelon form. Right, so now that we have this in echelon form, and let's actually solve it, Let's solve for x sub 1, x sub 2, x sub 3. Here we can see, we can actually translate that row 3 to be x sub 3 is equal to 3. How do I know? This is x sub 3, like I said, when we make everything to 0. X sub 2, x sub 3. This is x sub 1, x sub 2, x sub 3. Right? So it's kind of easy when we're back substituting x sub 3. That's 3. We could add a 1, but same thing. So now we go back. We go row 2. So negative x sub 2 plus 5x sub 3 is equal to, I'm going to replace x sub 3 with a 3. That's equal to negative 4. So solving this, we get 15, 19, 19. X sub 2 is 19. And then lastly, we go for x sub 1, which is, okay, x sub 1 minus 3 x sub 2 plus 2 x sub 3 is equal to, then we replace the values. So x sub 2 becomes 19, x sub 3 becomes 3, and this is equal to the right-hand side, negative 1. Then we can solve for x sub 1, which in this case is 50. So our solution are these guys. And we're done. We solved the linear system. Or we found the solution set, right? Great. And one way we can check is we can plug those 3 values back into the linear system, and we can see that they actually satisfy the original system. So we know they're true. Okay. Same idea. Let's do another example here. Right. So we find the solution set. Oh yeah, I forgot to mention. How many solutions does the system have? Apparently it only has one exact solution. Find solution set of linear system. So here we're actually gonna look at the linear system that we got earlier. So the one that I said we're gonna go back to. Look at this guy. Sure. That was scary. Gonna copy paste. Okay. So what am I gonna do? I'm gonna jump ahead of the textbook and I'm gonna convert these to a matrix. So we have 100, then 1, 930, 1, 2, 5, 50, 1, 145, 171, 117. Okay, I'm gonna do a couple of things actually. I'm gonna divide row 3 by 5? Think I can do that? Let me see. Because I brought a calculator. Okay, I could actually divide these things. So I'm gonna multiply 1/5 to row 3. What else can I divide? Can't divide these, no? Then okay. I'm just gonna do one thing here, I guess. Okay, now I divide this. 2 5 is 500. So I'm dividing 2 5 by 5. 50 by 5, that's 10. This is 1/5. This is 29. Right, just to simplify, right? Okay, what can I do now? I'm gonna multiply row 1 by 5 and subtract it to row 3. So what I'm gonna do, multiply row 1 by 5, subtract it to row 3, assign that difference to row 3. So I'm gonna say this is 500, 50, 5, 117 was that? 585. Okay. Then I'm gonna subtract it. So this becomes 0, 40. 5 minus a fifth. 5, 25 minus 24 over 5. And then 29, 556. Keep these. 931. Okay, what's next? Now I try to make this 0. So I'm actually going to rescale, put all of these back to 100, and 1, 117. I could do that, right? Now I'm going to multiply row 1 by 9, subtract it to row 2, and then assign that difference to row 2. So this becomes 999. 117 times 9, 1053. Okay. Then I subtract it to here. 900 minus 900. 90 minus 30, 60. 9 minus 1, 8. 1053. 1053 minus 171. 882. Let me copy. 24, 5, 5, 5, 6. Then we can rescale this, right? Oh, look at that. I can actually simplify one of the rows because I can see these are all even stuff. So I could say, I could actually do two things here. Row 2 could be divided by 2. So a half of row 2. Actually, a better notation would have been to assign that back. There we go. So we divide it by 2, we assign it to row 2. It's just proper notation. So we divide it by 2, we get right. Yeah, someone came in, so I'm just anyway. So great. Now we have the two zeros. We just want to make this thing is 0. How do we do that? Well, we have to do something with row 2. We want to make this thing a 40 or a negative 40. And then we want to interact it, or we want to apply it to row 3, make this thing a 0. Why can't we do it with row 1? Because then if we add row 1 to row 3, the issue is this. It's going to be a non-zero, right? So that was the strategy. So how do we make 30 a 40? We actually just multiply 40 divided by 30, right? Or in other words, 4 over 3. Because if we do that, this thing cancels. This becomes 40. Pretty intuitive, right? We want to multiply 4/3 to row 2. Okay? And then what that's going to do, it's going to make this thing a 40. Then we subtract that to row 3. And we assign that value to row 3. And even if we multiply 4/3 to 0, it's going to be a 0. And then 0 minus 0 is still a 0. So these are automatically zeros. Oh yeah, I could also just write row 1. Okay. And then 30 is going to become 40. So it becomes 0. This thing becomes a 40. 4 times 4/3, that's 16 over 3. 441. Can I divide it by any chance? Oh, I can. So 441 times 4/3 becomes 147. So it becomes 558 or 588. Yeah. I could keep row 3. No, actually, no. 16/3 minus 24 over 5. What do I do with that? Well, you want to find a common denominator. All I can think of is 15. So multiply all of these by 5. Yeah, just some fraction stuff. Times 3. 8 over 15. So it's not a bad number. Oh shoot, I didn't mean to put it there. There you go. So it's not such a bad number. And then 588 minus 556. That gives me a 32. Can I simplify anything here? No, I think everything's good. Then from there again, we can back substitution. So we get 8 over 15 x sub 3. Or no, shoot. This is c, right? So this is a, b, c. C equals 32. So we say that c is 32 times 15 over 8. Cancel these. 1, 4. I get c is 4 times 15. Gives me a 60. Right? See if I'm getting it right so far. Okay, so I got the 60 part. And then how do we get the b value? So actually, this is 40b plus 16 over 3c equals, and then we put 60, right? Can I divide this? Probably I can. It becomes a 1, becomes a 20. So actually, this is 20 plus 6, 20 times 16, 320. This thing is equal to, am I looking at the right thing? Yeah, 588. Then from there we see 268 divided by 40, 6.7. Is that right? Yeah. So B is 6.7. And then lastly, we look at A. So A is 100, 10, 1, 117. So 100 A plus 10 B plus 1 or plus C equals 117. And then actually, we can just plug in the values for B and C because we already know them. So 100, oh shoot, what was that? So 100A plus 10B, so 10, 6.7, that's 67, plus C, which I think is 60, right, is 117. Then from there, we say A is, doing all of those solving, we got A is negative 0.1. Right, so the solution is as follows: 0.1, 6.7, 60. Then going back to the projectile motion problem, we say, so E of x is actually this thing, 0.1 x squared plus 6.7x plus 60. So now we can actually model, we can see the behavior of the ball given 3 data points. That's the cool thing about linear algebra, right? That's the motion of the ball. And actually, we can show a picture of what that is. Then we can make some insights about the ball here. There's the ball. Or the projectile motion of the ball. So ball starts here, goes up, and lands there. You give it some x, it'll show you. So you give it an x value, say 60, it's going to show you, I don't know, just solve for e to the 60. So that's negative 0.1 times 60 squared. And we're going to solve that. 6.760 plus 60. And then that gives you a value, whatever that is. That's the elevation of the height, or that's the height of the ball at that particular x value. I would have named this t. I think it would have made more sense. Like at time here, that's where the ball is. But they chose to do it x and y. So that's them. I'm gonna label this actually. X. X. Okay. Oh, everything so far is making sense. Hopefully. We'll see. Okay. So we've done a couple of these. So I might actually, I'm still gonna go through it. Well, might as well, right? Okay, I have a couple of them. Yeah, I'm gonna go through these. Okay, so now we actually talk about the augmented matrix. So what in the world is this? Well, when we're manipulating systems of equations, the coefficients change, but the variables do not, right? And so we can simplify. So now we actually talk about it. We can simplify notation by transferring the coefficients to a matrix, which for the moment we can think of as a rectangular table of numbers. So when a matrix contains all the coefficients of a linear system, including the constant terms on the right side of each equation, it is called an augmented matrix. So let's just do an example, and I think, well, I don't think we need an example. But say we have this. So this thing is a linear system, right? I'm gonna do x sub 1 minus 5x sub 2 and minus x sub 3 equals 2 minus 4x sub 1 plus 13 x sub 2 minus 12 x sub 3 is equal to 11. That's within your system, right? What would be the augmented matrix? So this should be a bit simple. So we say the augmented matrix is 1, -3, 2, 2, -5, -1, -4, 13, -12, -1, 2, 11. That's an augmented matrix, right? We include the coefficients on the left-hand side as well as the constants on the right-hand side. Okay? Right. So, yes. So, augmented matrices include a vertical line separating the left and right-hand sides of the equations. What else can we say about it? Yeah, so now we talk about, well, it's a bit similar, elementary row operations. And honestly, it's the same thing. So I'm just gonna copy paste what I wrote here. But instead of equations, I'm just gonna change it row. That's the only difference, right? So equations, make it rows, multiply equation, multiply row, add a multiple of one row to another row, multiple. Yeah, yeah. Okay, that's the only difference, right? And again, we have equivalent matrices, right? So we say that two matrices are equivalent if one can be obtained from the other through a sequence of elementary row operations. Okay. Okay, let's actually look at some terms here because I know this is going to be on the test. Now, I have a feeling because they're making us do logical things. It's quite dumb. It's not a computational class. It's more of a logical reasoning class. Zero row, zero column. What in the world are these? So we say that rows are numbered from top to bottom and columns are numbered from left to right. So here's what it is. So a zero row is basically a row of all zeros. That's what it is. An example, I think we have one yet, but it could be something like this. This is a zero row. It's a row of all zeros, right? So that means a non-zero row basically contains at least one non-zero entry. When we say entry, we mean these guys. This is an entry. This is an entry. Entry, 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 entry. All of these are entries, right? Okay. So that's non-zero row. Now, zero column is, so these are the same, right? So a column of all zeros. Same idea. Then we also have a non-zero column. Amazing. We have everything here. Basically contains at least one non-zero entry. So that's what these mean. Okay. Okay, and then we have more examples. Do I do these? I'm thinking of not doing them, but you know what? It's okay. You have Gaussian elimination too. Okay, we'll talk about that in a bit. You know what? Let's just do it. You're gonna say example 3. So what are these? Or no, what's the example? So we find, or here we're being asked to find all solutions to linear system. Why is it showing that thing? That's so weird. I don't know if you guys can see that. Maybe it's because I'm in the textbook, that's why. Okay, so here's the linear system. We have 2x sub 1 minus 3x sub 2. You're kidding me. Plus 10x sub 3 equals negative 2. X squared. Oh, look at that. X squared minus 2x squared. Okay, plus 3x sub 3 is equal to negative 2. Then we have negative x sub 1 plus x sub 3, or 3x sub 3, plus x sub 3 equals 4. So immediately what I'm going to do, I see 2x sub 2's here. I'm just going to add them both. So we got negative x sub 2, right? So we just did, shoot, what was it? Yeah, we did x sub 2 minus 2x sub 2, factor out the x sub 2, 1 minus 2 x sub 2. We had negative 1 times x sub 2. That's it. Or a simpler way, we just treat that like a number. So we just do 1 minus 2. It's really simple. Okay, so now that we have this, oh, another thing. Look at that. 3x sub 3 plus x sub 3. That gives me a 4x sub 3, right? It's going to be a 4. Cool. Okay. This is going to be funny. So I'm immediately going to convert that into an augmented matrix, right? 2, negative 3, 10. Now the rows don't matter. Like the order doesn't really matter. What matters is we want to make them all, we want to get this to echelon form. So the second row doesn't have an x sub 1, so we make it a 0. Right? And we keep going. Negative 1, 0, 4. And there we go. Now, personally, how I would switch this up, I would switch. Let me think. Yeah, I would do row. So there are a couple of ways you can do this. I'm just gonna do it how I think is convenient for me. I'm gonna switch row 1 with row 3. So that's the notation for that. It becomes like this. This remains. I want to put this down though. Uh-oh. I did not mean to do that. 2, then 2. And then what I plan to do is switch row 2 and 3. That way, I put 0 down here. So just a little bit of looking. Yeah. So those are the two things I would do, but it really depends on what your preference is. So I would switch row 1 and 3, then switch row 2 and 3. So now I have this, and nothing changed, right? We just switched a couple of things. I just want to make it so that I can remove these two, right? Okay, let's actually do that. So let's make this thing a 0. I'm going to multiply row 1 by 2 to get to -2, right? And then I'm going to add that to row 2. And then assign that value to row 2. So let me just do that. So we do -2, 0, 8, 8. Okay. Then we have, so we added, we got 0 here. I could copy row 3 because I'm not doing anything with it. -3. 0 minus 3 is -3. 10. 8 plus 10 is 18. 8 minus 2 is 6. Okay, looks about right. Now I could rescale this thing. Make it to 1, 4, 4. Okay, right. What's next? Now I want to make this thing a 0. So I have to do something to row 2. I can multiply a third, right? -1/3 to make it +1. Then I could just add it to row 3. Then add that to row 3, right? There are a lot of ways you could do this, but really, this is the way I'm thinking of. Then these two are 0, so we got that covered. This one's going to be a 1. This one's going to be a -6. This one's a -2. Well, that's actually nice, because you could divide everything by 3. 1 minus 1 is 0. 18, or no, -6 plus 3 is -3. Is that right? Yeah. -2 plus -2 is -4. Yeah, I'm gonna leave this as it is because it's nicer. Could put it back to here, but this one's nicer. Now we have it in row echelon form, right? Now I can safely back substitute. Okay. All right. Textbook says there's a general solution. I don't think there is. But we'll see. I think there is though. I messed something up. Okay, so let's just go for it. -3 x sub 3 is -4. I could just divide. X sub 3 is 4/3. Oh, interesting. Wait, am I solving the right thing? 2 minus 3, 10. 1 minus 2. Oh, wait. What did I do? 1. Oh, he's wrong. Yeah, textbook's wrong. You didn't position them correctly. Yeah, textbook's wrong. Okay, 'cause I did simplify this. But if I were, yeah, textbook was wrong in the beginning. Anyway, let me just continue this. Okay, so then we have x sub 2 minus 6 x sub 3. Then we say x sub 2 minus 6 or third. Then we have 8. This becomes a 1, becomes a 2. Minus 8 equals something. Negative 2. It's actually 8 minus 2, 6. X sub 2 is a 6. X sub 1 minus. Then this is a plus 4x sub 3 is equal to negative x sub 1 plus 4 times x sub 3 is 4 thirds, right? This is 4. So we actually have 16 thirds. 4 minus 16 thirds. 16 thirds minus 4. I don't know. 3, 12, 4 thirds. So in this case, x sub 1 and x sub 3 are equal. So our solution is 4 thirds, 6, 4 thirds. Okay. There is, yeah, so there is one where there's general solutions, but we're not going to go through that yet. Okay, so that's it for today's video. I think we've done a lot of problems, mostly on elementary operations. We're introduced to the augmented matrix, so now I'm taking it a bit slow and more relaxed. And I hope you guys learned something, enjoyed, and I'll see you all in the next one.